Hello, everyone. My name is Peter Boza. I work at a company called Vision Analytical, and today I will be discussing using a new approach to a measurement method for the crystallization process to get some quantitative, not just qualitative, but quantitative analysis using dynamic image analysis. So I'm sure this is very well known by the audience, being that this is a pharmaceutical conference. But just to give a slight little overview, crystallization is a process for purification. It's used in many many different chemical industries, and it is definitely used quite a bit in the pharmaceutical industry, primarily for the separation and purification of APIs. There are many conditions that are used to creating these crystals. There are conditions having to do with temperature, pressure, saturation, with different solvents that are used. So I think the crystallization process is very unique to every application. But basically, the idea behind crystallization is similar, where we're looking for a good purification process to get an API. The monitoring of the kinetics of crystal growth is very important. This is something that's always been sought after by pharmaceutical chemists, where they're looking for the nucleation rate point where they're growing the crystals, whether it be out of solution as a primary nucleation, or even out of other crystals, looking at secondary nucleation, when that happens, what conditions are active at that point, and monitoring that whole process has always been very important to crystallization chemists, especially in the pharmaceutical industry. One of the things that we're going to be talking about today is one of the tools that's used for monitoring this crystallization process, which is particle size analysis. So particle size, or crystal size, is something that's always been looked at, in addition to other things that are looked at in the crystallization process. But today we're going to be talking about primarily particle size. We'll look at some of the current tools, and then we'll look at this new idea, this new concept of particle size for the crystallization industry. So going over a few of the current methods that are used. One current method, which is extremely popular, is laser diffraction. Laser diffraction is a very well established method, very well known, very easy to use. It is an offline method. Because it's an offline method, it does require the user to take specific aliquots of sample during the crystallization process. That's a dynamic process, and do the preparation and suspension to actually analyze it in laser diffraction instruments. So that's a bit of a challenge, because it's a growth process. The crystals keep on growing. You might be changing the environment it's in when you're doing the analysis with laser diffraction. So there has always been some concerns. Still, it's a very popular tool because it's so well established. In addition, one of the other things of consideration is that laser diffraction, along with many other techniques in the industry, is an indirect measurement technique. So what it does is it measures the angle of scattered light from the particle. As a result of that, the particle size is only represented as a spherical particle, as a round particle. So that's another thing that has to be contended with, is when you're doing size measurements with laser diffraction, you will get differences in size, but it always assumes the particles are round. Okay, so that's one very well-known method. Another very common method, especially for the crystallization industry, is what's called FBRM. And FBRM is an inline probe. It is used quite a bit for the pharmaceutical industry. And what the inline probe does with a rotating optics component, it will give you a chord length of particles. So as you can see here on this screen, there is an example taken from a paper that was written and from the manufacturer, where it will actually look at the actual chord length of particles where it can distinguish a chord length. That's a bit of a challenge because if you think about it, if you look at a crystal here on the right, if you look at a crystal, if the crystal rotates, gets in front of the laser in one angle, it might report one size. If it goes at different angles, it might report a different size. Also, with the translucence of some of the crystals, it's also very difficult to get the true size of the particle. So that's one of the limitations with FBRM, but still it's a very established method because it's used quite a bit in the crystallization in the reactor industry. One of the other very popular methods is microscopy. There are two types of microscopy. There is inline microscopy. It's relatively new. It's a probe where you actually put in a optics probe into a reactor. You do a measurement, and it is a very good tool to get qualitative analysis. So just to give you an idea of what's going on in your reactor. It's good to know what's going on in your reactor, although trying to get a lot of extracted quantitative information is a bit of a challenge. And representative sampling is also a bit of a concern. And then we also have offline microscopy, very similar to other offline techniques. Again, it requires you to take these samples from the actual reactor and do an analysis. And again, requires prep, making sure that the crystals don't continue to grow. And then representative sampling is also a bit of a concern as well. So there's a lot of techniques out there, and they all work good, but the challenge that we were faced with is more is better, right? So the whole concept of more is better is always something to look at. These are all excellent tools. They're all very efficient. They're all very effective for what they do. However, many scientists have always expressed the need for something a little bit more quantitative, especially during the entire kinetic process of crystallization. So what we're going to be discussing here in the rest of the presentation is the use of an adapted at-line technique, and it's being used in an in-process manner. And the ultimate goal is to get image analysis to distinguish the particles from the background in a very dispersed way, in a continuous way, in real time, to give you the quantitative analysis. So let's talk just really briefly about dynamic image analysis, and then we'll go into two short videos. So the benefits of dynamic image analysis, there's several. First of all, dynamic image analysis is a direct measurement technique. By direct measurement technique, what we mean is we're actually measuring the actual particle. So by having the particles dispersed, the actual particles can be imaged, and then they can be measured. So you get the true size. We can give you different types of sizes of whether it be equivalent circular sizes. We can give you aspect ratio, circularity, so many different types of shape information. So the benefit of having all the shape calculations for all the particles really is to enable the end user to differentiate one from the other a lot easier. So you may be able to look at the differences between the beginning of a crystallization process and the end based on not only size but maybe aspect ratio or both, or also including opacity, how dark the particles are. You can differentiate bubbles based on their circularity and their opacity. So there are a lot of different uses for attributing so many different shape factors to every image that's captured. The particles are in motion, so it's all captured all in real time, and the information is also captured alongside with temperature. So as the temperature changes, which is a very common use for a very common trigger for crystallization, the temperature is also tracked, so we can actually determine to see what changes in crystallization are happening over time. And then of course we get number-based results where we actually analyze every single particle, and the fact that we actually have thumbnails at the end for objective evidence is also very helpful. Okay. So the setup that we have, the experimental setup that we had made was a experimental setup where you actually have a reactor here that's actually crystallizing some sample, and we have an instrument located with some insulated tubing very close to the reactor. Often these reactors are going to be sitting in fume hoods, so it's very, having real estate for equipment is very challenging. So having everything in a small package is very ideal. And then all the computational work is done with a battery backed up cart where the sample is viewed on the screen, and it's all real time. It's touch screen, so you don't really need to have you could operate everything with a touch screen interface, and it could be about 3 meters away. So you have this tether that you can actually have it 3 meters away, not taking up space inside the fume hood. So the sample is actually drawn through a sample cell, a very thin sample cell. There's different sample cells you can select, and the fact that you run it in through a sample cell allows it to disperse the particle, and then the sample is returned. And we did notice that there's really no difference in temperature by having a sample aliquot taken in and pushed right back in. So nothing is done inside the instrument to alter the sample. The sample is just drawn in, the analysis is made, and it's put right back. Okay, so that's the actual physical setup. To look a little bit more as to what the actual instrument does as far as the live view, here's a good example of what the live view is doing. The live view shows that we have here on the right hand side the trend charts, we have histograms, and then we have the actual images being taken. So the images being taken, as you can see, they're somewhat dispersed, and as time goes on, you'll notice that the crystals are getting larger and larger. Every time that there is an analysis done, it's a sequential set of analysis. So for every dot that you see on these trend charts, you'll see it's a sequential run. The trend charts capture up to 4 different measurements. One of them obviously is very practical to be temperature, and there's concentration, because the instrument, because it's a number-based instrument, we can give you volumetric concentration. So we'll see the concentration increasing as we see also the size increasing as the temperature decreases. So the trend charts show the changes over time. You have all the histograms. So every time an image is taken, all the thumbnails, there might be hundreds of thumbnails every time there's an image taken. Each one of those thumbnails is captured, and up to 32 or 33 different shape measurements are made for every single particle, and it's stored. After the fact, there are many things that you can do. After the fact, you can go in, you can look at the actual thumbnails, you can look at the histograms. Typically, it's interesting to look at the thumbnails, but it's also very interesting to see if there's anything in the trend that changed that was of interest. If there is anything in the trend that is of interest, the user can actually go in, look at that specific run, and look at the specific thumbnails that attributed to some specific change in the trend chart. So again, if I had to go into one sample here that's an outlier, I can go into that one run. I could look at the thumbnails, I could look at all the statistics and the data for that one run. And again, you have the objective evidence of having the thumbnails, which is a very valuable factor for looking at the results. So getting to the end of the presentation, why did we do this? I think this is probably the funnest slide of the entire presentation. We did this because the concept was originally initiated by a pharmaceutical company that was looking for more information. More is better. So they wanted more information, and they had at-line instrumentation that they felt could give it to them. They just wanted to find out what can be done to implement that. So they created a collaboration. So they decided they're going to break down whatever barriers they have. They're going to work with us, and we're going to work with them to see if there's any way of figuring out how to give them more information. So that's how the whole thing came around, and that's how this whole project came about. What's next for us? What's next for us is to continue to listen to customers and users, and making improvements and making them fast. So that's our goal. and we will continue to do that. And the moral of the story, at least of this whole project, is, don't don't let something or the norm stop you from trying to look for alternative ways of implementing solutions to give more information, which leads to the fact of what's next for you. So how are you going to try to adapt maybe a barrier to some analysis problem that you might be experiencing in your lab, and seeing how you can actually implement something that maybe is different out of the norm to try to satisfy your requirements. So I invite you all to look and try to see and just keep at it. There's always a way around it. I'd like to thank everybody. If there's any questions, please contact me. Thank you very much, and thank you for the Forge for putting together this excellent presentation.